We're going to be looking at line spectra. This is a part of quantum physics where it helps us to explain a little bit about the electron energy levels of an atom and how that acts with light. So, let's take a look. If white light, and remember that white light is a combination of all types of wavelengths, when this is passed through a diffraction grating, a continuous spectrum is seen. And this you probably did learn before. If you pass it through, then the light gets diffracted, and you get this continuous spectrum of all sorts of colors, and each color represents a different wavelength of light. What's interesting is that when you have lamps that contain hot gases, like neon or sodium, only certain colors are present. So only certain colors are emitted by these lamps that contain these hot gases. Take a look at this. So we can take the light from the lamp, we can make that source, and we can make it narrow. And then we can pass it through a diffraction grating again. If you do that, it's going to spread out onto a screen, right? That's when a line spectrum is seen. And this is a line spectrum. So usually for white light, if you spread it out, you have this continuous spectrum. But if you take the light that is from these hot gas lamps, then you're going to get only certain colors of light for each element. For instance, hydrogen only has this purple color, this blue color, and this red color, and maybe a few faint colors here and there. For helium, you have these. For argon, you have these. For nitrogen, you have quite a lot of colors. And so you can see that each element has a very unique line spectrum. Each hot gas only emits certain colors, and that is where the interesting thing about line spectra come from. And line spectra is the plural form of line spectrum, right? So as I said, each element has a unique collection of wavelengths, right? Colors equals wavelengths in terms of visible light. This can be used to deduce elements in stars. So what we basically use to probe stars and to look and learn about the different types of things that are in the universe in astrophysics is through light, because there's no other thing that travels far enough for us to be able to observe it. It's very hard for us, for instance, to observe the sound that's coming from them because it wouldn't travel through vacuum in the first place, and even if it did, it probably would not reach us. It would disperse. And we do have things like gravitational waves, but the most abundant thing that is the easiest for us to probe is through light. And we use this knowledge about line spectra to investigate different types of stars. And you can very much guess how that happens. You look at whatever color light is coming from a certain distant star. For instance, if you have this pattern that's coming, you have red and blue and purple in this very specific shade, right? And this very specific shade would translate to a very specific wavelength. Once you realize that these three are coming out, you can then deduce, oh, this has how much hydrogen. And so that's very important for that reason. Now, these are emission line spectra. What that means is, remember the word hot gases. These are hot gas lamps. We know that hot gases have high energy, right? And therefore, the electrons of these gases have high energy. What they do is that they emit light as energy because they have such high energy in the first place. And that's why they have certain light that is emitted. So they emit these sorts of light. However, we have another type of line spectra, and this is called absorption line spectra. Now, this is produced when white light is passed through cool gases, and certain wavelengths have been absorbed. So, while over here you make light and you emit light, over here you pass light through something and certain wavelengths are absorbed. So this absorption line spectra can be used to analyze the cooler outer layers of the stars. And the very hot interior of the star would emit white light, right? Because there's so much light that it emits light of all sorts of wavelengths. And when this white light passes through the cooler outer layer, then only certain wavelengths would be absorbed. And so we would get absorption spectrums with which we can use to guess the sort of elements that are present in the cooler outer layers of a star. So it is important to see the difference between continuous spectra, absorption spectra, and emission spectra. They come from different methods, right? But interestingly, each element is the same. So these two are the same elements. They're either the same colors are either emitted or absorbed for each element, and that's what's interesting. So let's talk about it. Why do different elements emit and absorb different wavelengths? Well, two things to first consider before we really dive into the question. And that is, we consider light in this situation to act as photons and as particles. We're not talking about light as waves, but as photons. And therefore, the equations that we use is Planck constant times the frequency equals energy, which is also the same with this. Second thing to take note of, when light interacts with matter, electrons are going to absorb energy. That is, absorb light. When electrons lose energy, light is emitted by matter in the form of photons, which is what we just said. So the line spectra tell us that electrons in atoms only absorb and emit photons of certain energies. This can be only explained if we also conclude that electrons themselves have fixed values of energy. If they have fixed possible values of energy, they need to jump from one energy to another, and therefore they can only emit and absorb certain wavelengths of light, certain energies of light, never more, never less, or never in between. And so we draw this, which is the energy level. This is the energy level of hydrogen. And what's interesting is that these are energies, right? 0 joules, negative 0.06 times 10 to the power of negative 18 joules, and so on and so forth. And the hydrogen atom's electrons can only have one of the energy levels, and this one people have deduced using the line spectra. So that means that electrons can't have negative 0.07 joules. That would be somewhere around here, right? They can't have that. This is forbidden. They can only have one of these. It's like a ladder. You cannot put your hand through the lungs of a ladder and expect to go up. You need to hold on to the ladder. So this is what it is. And we conclude that through the line spectra, we can conclude that electrons can only jump between these states, never in between. So this is why they have only certain fixed wavelengths that they emit and absorb. They can only jump between here and here, and maybe like here and here and here and here, and therefore this is each one wavelength, right? But you can't ever have these like continuous wavelengths of like all this. That's impossible. So this explains the line spectra. So the values are negative, as you can see right here. The values are all negative, and at 0 joules, they are freed. Now, the reason why they're negative is because these electrons, when they have these energies, it means that they're quote-to-quote trapped. They're trapped inside the atom. They're bound to the atom by the electrostatic attractive force between the electron and the nucleus. You need to do work against the attractive forces in order to give it 0 joules, right? You need to do work against it in order to free it. Therefore, they have negative energy when they're bound to the atom. The distinctive energy levels of an atom mean that the energy of the photons emitted, and hence the wavelengths emitted, will be unique to that atom. So that's how the line spectra and this energy level thing is all bound together. So picture this, if the electron makes a transition to a lower energy level, let's say we have an electron, let me make that red. We have an electron right here, and it makes a transition to a lower energy level. The loss of the energy of the electron is the difference in the energy between this and this. So let's pull out our calculator. What is negative 2.18 minus negative 0.54? That is negative 1.64 times 10 to the power of negative 18. So the energy of the photon has changed by this much. It has decreased by this much as it moved down, which means that the photon that has been emitted will have this much energy because energy has to be conserved. What if this electron moves up a little bit? How much do you have to add for that to happen? Well, you would have to do 0.54 minus 0.34, and that is 0.3 times 10 to the power of negative 18 joules. And we're keeping to this thing right here. So it's 10 to the power of negative 18. So you need this much or more energy for it to jump up here, which means that it has absorbed a photon that has exactly this much energy, so that the maths can work out and that the conservation of energy can be followed. So all the mathsy stuff brings us to photon energies, and we have already established before in the video about the photoelectric effect that only one photon can react with one electron, because we're talking about photons as particles. So they are distinct. There's only one that interacts with one. And when these interactions happen between light and matter, this is a one-to-one interaction, which means that the photon energy of a single photon, never 2 or never 3 or never 1.2 or 2.1, but always one photon, has to be the change in energy of the electron, which is also represented as delta E. Now, the change in energy of the electron is, as we said, very simple. You just have to take a look at the energy level diagram, and you have to see the jump that it took. How big the jump is, that's basically delta E. And when you know delta E, you can have the photon energy, which is Planck's constant times the frequency. So you take the initial one minus the final one, whatever, you just get the difference in energy, and then you figure out what the energy of the photon has to be that interacts with it. Now, as we know, this is exchangeable with this, because frequency is V over lambda, and because we're talking about light, V can only be 3 times 10 to the power of 8 meters per second. So this is also denoted as C. So F is C out of lambda, and that's why we put it in here, right? So this is also an alternative, but ultimately these are just the exact same equations. And this makes a lot of sense when you realize that this is a one-to-one interaction and electrons can only have distinct energy levels. Another thing to note, and one final note, is that the lowest energy level is called the ground state. So what is the ground state for hydrogen? Well, we can go back to the previous slide. The ground state is here. This is the lowest because they're all negative numbers, right? So whatever has the biggest magnitude in the negative numbers scale would be the smallest number, right? So the ground level is negative 2.18 times 10 to the power of negative 18 joules for hydrogen. So that's it for this video on line spectra, and they actually teach us a surprising lot about it. I hope that this helped you in some sort of way, and if you want to have more videos on physics at the A level similar to this one, then do check out the other videos I've posted on my channel, and thank you for watching.